You're welcome to Radioactivity Part 2. Remember, you have to go through the first radioactivity for you to understand what is radioactivity, but we are going to try our best in this section of this lesson to throw more light for a better understanding. When we talk about radioactivity, but before then, let's look at our specific objectives. You have to define radioactivity, then state the radioactivity decay, that's supposed to be state the radioactivity decay, prove the activity formula and the half-life formula, sketch a curve of decay, and solve few problems on radioactivity. Let's keep going. Radioactivity is the spontaneous decay or disintegration of the nucleus of atom of an element during which alpha, beta, or gamma, or a combination of any of the three of the particles with the release of energy. So most of the things we said in the part 1, we are just trying to talk about the theoretical understanding of what radioactivity is all about. So most of the things we are going to do now is the application in mathematics. Therefore, radioactive law. We have to first of all understand the radioactive law, which will be the basis for our calculation. We said that this law says that the number of radioactive decay or radioactive nuclei decaying per time. So whenever in mathematics we now use d of a variable all over time, it's talking about change in the quantity of in a particular quantity with respect to change in time. Just like I want to give you, for example, when you talk about, we said that distance is equal to velocity times time. We also said that velocity is equal to displacement over time. All right, in this case, you remember that whenever distance is changing, time will always change as well. So that is why they always say that velocity is the same thing as dx dt, when x is seen as a displacement. So we are going to have that full understanding in what you are going to do. So your knowledge of calculus is very important. Now you said that the law states that the number of radioactive nuclei decaying per time is directly proportional to the number of nuclei n present at a given time. So if something started at 1,000, let's go straight to, you know, how you spend your money. For example, let's assume you have 1,000, all right? And let's say that particular day is on Monday. So on, let's say, Wednesday, of course, you are still not going to have 1,000 left because you are spending. So what are we looking at? You are saying the quantity of what you have depending on what you are spending per day. Let's assume on Monday you spend, let's say, 200 on Monday. Then on Tuesday, you spend another 200. So what will be left at this point? You have spent how much? 400. You spent 400 of this amount on a Tuesday. So this is what is remaining. No, this is what you have spent so far. So the quantity was 1,000, but what you are left now is 400 on a Tuesday. Therefore, on Wednesday, what will be left? Of course, not left. I mean, what is the quantity present? Because we are looking at present quantity at a given time. So the quantity present here is going to be 600. Because why? You are spending 200 each day. So that is what is left at that given time. Therefore, when we look at this particular radioactive decay, we say what is decaying at a given time and what is left at also a given time, the instantaneous quantity left. Therefore, we are going to use calculus to explain the concept better. Now, this law, therefore, we are going to say that dn all over dt is directly proportional to n, because this is what is left, right? But then we are going to use a negative sign to show that actually it is decreasing in value. It is not increasing. So if it is increasing in value, then you can, be proud of it. But in this case, it's decreasing. Therefore, I'm going to use a negative sign. I'm going to use negative sign to represent it. But then, remember in mathematics that when you are using proportionality, you are going to do what? You're going to make sure that it is removed. Therefore, we are going to say that dn over dt is equal to k minus kn. This negative has to be there. But in this case, this constant of proportionality, I'm not using k. I'm going to use a symbol called alpha. If I say that k is given as alpha, therefore dn dt is going to be equal to minus alpha n. So this is exactly what radioactivity is talking about. So we are going to use this now to do a derivative for what we are yet to see. So if in this case you are looking for equation, maybe a question is given to you, the number of quantity decaying at a given time is equal to the number left. If there is a constant of proportionality, which is called decay constant, we are going into that point. So now we are going to prove that the activity formula is given as this. Sometimes depending on the textbook, because whatever we are going to prove there is starting from where I left off here. Sometimes some people use it as activity. They say A is equal to A naught, A sub 0, E negative. Remember, this is still this one, which is called the decay constant. Now, how are we going to do this? Let's start. We are going to take it slow and slow for us to be able to understand every step as we are going. Therefore, I'm going to, for me to prove this, I will start from here. So I'm going to say that the n dt is equal to minus this. All right? Okay. In this case, remember n naught. This m naught means the quality or the quantity of the material at time 0. That means the whole value of the element. Like I said in my explanation before, your whole 1000, when you did not spend, when there was no time spent. And what is n? N is what is remaining after this time. Therefore, this n is a function of this time and the value of the element at a given time. So, for us to keep going now, we have to do important thing. What we have to do is to let us clear this fraction, all right? Let us clear this fraction. We are clearing the fraction. We are going to say that dn is equal to negative alpha n dt. Now, remember in calculus, it's not good that you are having a number, a particular quantity, who has its dn. Let me explain what I mean. If you want to have v, you should have the v. Then integrating it will be easier and very, very good. In the sense that I cannot have p and you are telling me p dv. That means I'll be expressing this p as a constant or not a quantity of which v is given a responsibility for. So what I'm going to do now, for me to achieve that, I'm going to separate the variable as if I'm doing a ordinary differential equation. So this n has to come this way. So I'm going to divide both sides by n. Therefore, I'm going to have dn over n is equal to minus the k constant dt. Like I told you, this now is a constant, which we know. Now, for us to be able to break this down, I'm going to integrate this side and also integrate this side. Remember something about integration. If you are asked to integrate 1 over x, remember what it is going to be what? In x. If you also say, sorry, it should be this. Therefore, the same thing we are going to do here. Because this is something as 1 over n, the n is something as this. But this integration, I'm not just going to do this kind of integration, which is, we are going to do a definite integration, in the sense that this thing started from somewhere and is ending at somewhere. So remember. So this started from n sub naught, which is the total quantity of the radioactive element at the beginning when the time was not started counting. And then it stops somewhere when the number of the quantity present at a given time. This is the number present at a given time, all right? The same thing happens. This one must also start from time 0, so T naught. So this is going to start from T sub 0 to a particular time which we don't know. We are looking for that particular time. It could be after 5 years, it could be after 1,000 years, it could be after 5,000 years. So we don't know. So let us do that here. Therefore, to continue with this, what I'm going to do, integrating 1 over n with respect to n, I'm going to have in n, right? But in this case, I'm going to do a definite integral, which is from the beginning to a particular quantity left. And this is equal to, also remember, for me to integrate this is a constant, they must go out. So I'm going to have, this is going to be equal to minus alpha integrating dt. Remember, if I'm integrating dt, I'm going to have t left. Therefore, this is going to be equal to minus this t from t naught to a given time. So this is what, so everything here is this. So I'm going to have minus alpha t from a particular time, time 0, time naught, to a particular time, which I don't know. So what will I do? I will substitute this and this into this. So that is what we are going to do in this case. So to do that, I already have what, so I'm going to start from highest to lowest, highest to lowest. So I'm going to have in n minus in sub naught, okay? So I substituted, for anywhere I see n, I will put this and subtract, put the next one. So for this one also, I'm going to have minus lambda bracket t minus lambda bracket t naught. Okay? So I'll opening the bracket. So this is in minus in naught is equal to minus lambda t plus 0, because this is time 0. It is actually, no time was recorded at that t. So everything here is going to be 0. So we have this. Now remember something about logarithms, because remember this in is something as log base e. Now log base e, if you have log n base e minus log no base e, remember it can be log, according to rules of logarithm, subtraction can be division. So I'm going to say n over n sub naught e, which is also going to be the same thing, in n all over in naught. So that is what I'm going to do here, okay? So I'm only telling you that this is this for you to. So I'm going to have in n all over n naught, which is equal to minus this. Now remember if you have log 8 base 2 is equal to x, what will happen? The one on this side will come on, you have 2 raised to power x is equal to 8. The same thing we are going to do here. All right? The same thing we are going to do here. But let me use this better for you to understand. I'm removing this, I'm using the other one, log base E, n all over n naught, so that some of us will understand it better. Therefore, applying what I just did, everything here will come on top of this. So it's going to be n all over n sub 0 is going to be equal to E raised to power minus the constant and t, right? So when I clear the fraction, I have that n is equal to n sub naught E minus raised to power minus lambda t. And this is the proof for this formula. So knowing how this came about, I am sure using it to solve a problem will also not be as hard. So let's go to the next one. We say half-life. We can also show that half-life is this, right? Let's check if that would be, if we can do that easily. So at half-life, okay, so what we have now is pure that what we have now is this. So at this point now, what is going to be half-life? Half-life is actually the time it takes for half. Okay, let's go to that next slide. The time it takes half of the original quantity to decay. Therefore, at that point, what will be remaining is going to be n naught over 2. You know, this is the original quantity. If you divide it by 2, that's what will be remaining. Just like you having 1,000. If you divide it by 2, you are going to have 500. So, but since the original quantity we don't know, so we are going to be using it this way. So I'm going to have, for this, what will be remaining is going to be this 500 or this. Therefore, instead of this place, I'm adding this. I'm going to say n naught over 2 is equal to this minus this. Okay, now at this point, remember I am free to do this. So I have 1 over 2 is equal to this minus lambda t. Now at this point, this time, remember, is the time t unknown. So for me to be able to solve this, I still have to bring in logarithms, okay? So I'm going to be taking log e to both sides, log base e of both sides. So this is going to be log base e, and this is also going to be log base e. Please pardon me, this should be in front. Let me write it better. This is log base e, which is e minus raised to power minus lambda t. All right, so according to logarithms, you remember this is tempting as in. So instead of writing this, I can also say that it's going to be in 1 over 2. Remember, this is tempting as this. All right, I'm using a more friendly parameter. So in this case, I'm going to be looking for in 1 over 2. Okay, or also another thing we are going to do is saying that this is going to be in 1 minus in 2, which is equal to, remember, no confusion, this is going to be log 1 base 2 base e minus log 2 base e. Remember, the division is the reason why I'm putting this, and this is going to be equal to, remember also, when you have a logarithm, what happens to the power? The power will come down and multiply the logarithm. I'm having negative lambda t log e base e. Now remember, log to each base is what? Is 1. So everything here is going to be 1. So log 1 to any base is 0. Therefore, this is 0. We have minus log 2 base e is equal to, everything here is 1. Minus lambda t times 1 is also minus lambda t. So what do we have left? What we have left is minus in, okay, let me go back to in 2. Remember, I can use them interchangeably, but in a singular solution, you should use 1, which is uniform. So that's, in that case, I'm going to have minus log 2 base e, which is going to be equal to minus lambda t. So let's find what is this, right? So I'm using the calculator to find what that is. Okay, so we are going to have, this is going to be minus 0.693 which is going to be minus lambda t. Remember, this t is the time for the half-life, which we are looking for, which I want to make the subject formula. So minus cancels minus. So t 1 over 2 sub 1 over 2 is going to be equal to 0.693 all over lambda. So this is the time half-life of any radioactive element, whereby this is that decay constant. So we have what is half-life and also a decay constant here. So we are going to use them to be solving a few questions as we move on. Okay? Then we can also have other approach to the solution as well. Now we have the first question here. We say a sample of radioactive material has a half-life of 20 hours. What proportion of the original radioactive nuclei will remain after 80 hours? What proportion will remain after 80 hours? So when we talk about the proportion, we are looking at the fraction. So the proportion, we are going to, let's go back to the original equation where we said this is n equal to n naught e raised to power minus lambda t. So at this point, I am going to say that I will divide both sides by n. So n all over n naught is equal to e minus lambda t. All right? So in this case, the time left is this, 80. But then we can find this value. We can find this value now using this formula. But before then, let's not complicate issue. But before then, let's do it this way. Let's do it this way. We have that a sample of radioactive element has a half-life of 20. So if I say that this is 20, this is n sub naught. Okay, let me use this kind of line. We have this. This is for time and the quantity. So at this point, time is 0. All right? This is the beginning in a scale. As this is moving this way, this is scale. So after the first half-life, and that half-life is what? 20. After the first 20 hours, what will be left of this quantity is going to be divided by 2. So this is going to be n naught over 2 after 20 hours. We are starting from here. This is the beginning. After 20 hours, that original quantity, which I don't know, is remaining half. All right? After another 20 from the beginning, this is 20. Another 20 is going to be 40 at this point. What will be left? Half of this one. So that is going to be n naught over 2 times 1 over 2, which is going to be n naught all over 4. So after 40 hours, I'm going to have n naught all over 4. So it's reducing, keeps reducing, like a sequence. Then after another 20 hours, which is going to make it 60, what will happen? This is going to have 1 over 8. How? Because this is going to be times 1 over 2, which is going to be n naught all over 8. All right? Then, after another 20 hours, we have what? 80 at this point, and what is left? N naught all over 16. All right? Therefore, when the time has reached 80 hours, the quantity that is left is what? N naught over 16, which is something as saying 1 over 16 of the original quantity is left, is remaining after 80 hours. So this can be done. We can also use the formula which I have just proven to do this, but for the sake of simplicity, we are working with this. Because most of the times our students will say, so why not use that simpler approach? So that is why I'm doing this way. We also have, let's look at this question. It said, the decay constant of isotope of a nuclei is 1.36 times 10 raised to the minus 4. It said calculate its half-life. All right? Okay, I think we also have to go back to this formula. Remember the half-life, T-half is 0.693 all over okay, all over, and this is lambda. So we say we should find the decay constant. Remember, this value is the decay constant. So the decay constant of a radioactive isomer. Okay, we already have this. They have given it to us. So I'm going to have T 1 over 2 is going to be 0.693 all over. The decay constant there is going to be 0.123. So I'm converting that to I'm converting it to indices. This is going to be 1, 2, 3, 4. And that is it. So when we divide this, we are going to find the half-life. 0.693 divided by 0.000136. So the half-life is, I'm having here T half is going to be 595.6 seconds, because since it's seconds we are dealing with, it's going to be seconds. So this is going to be the half-life of this problem. Thank you for being part of this class, but remember we have series of questions according to Examguide app, which has been set by different exam bodies. So we are going to check a lot of questions there as pertain to this topic. Okay, we have series of questions here. Remember, this is radioactivity part 2. So some questions on fission or other radioactivity part 1 may be interfering, but we choose the one that best suits our lesson. So we go further, we said, okay. Okay, a radioactive element has a decay constant of this, calculate its half-life. We have done a question that looks like this. So, but then let's look at this question. T half-life is equal to 0.693 all over lambda. So T half-life is going to be 0.693 all over 0.077, 0.077. So 0.693 divided by 0.077. And 9, do we have 9? Okay, we have 9 seconds, and that is option C. So this is 9 seconds. Okay, so let's look for something that looks okay. We have a radioactive substance has a half-life of 3 days. If a mass of 1.55 grams of this substance is left after decaying for 15 days, determine the original value of the mass. Okay, like I told you, I will always use the one that students prefer so much by experience. So, like I said, I will prefer this method that is easy for comprehension for students. Probably when I'll be doing radioactivity part 3, I'll be using most of this activity formula in my problem solving. But let's do it this way. Let's assume, let me use it as scale. Maybe somebody will understand this better. At this beginning part, 2 things will be happening. The quantity at this point, when time is 0, is the same thing. What I mean is that this quantity has not started decaying because time has not started reading. Now, when time reads, the first time, which is 3 days, which is half-life. So after half-life, half of this thing will be left. So this is going to be 3 because the half-life there is 3 days. So after 3 days, this one will be 1 over 2 of the original will be left. So it's going to be NO over 2. Then after another 3 days, another time, 3 days, which is 6, because 3 plus 3 is going to be 6. So what will be left here is going to be, if I multiply NO over 2 times 2 times 1 over 2, I'm going to have 1 over 4. Remember, N sub 0, that is the original value. Then after another 3 days, which will be 9 days, I'm going to multiply this one by 1 over 2, which will give me N sub 0 over 8. After another 3 days, this will be 12, and that will be n sub 0 over 16, multiplying by 1 over 2. So after another 3 days, I'll have 15 days, and then I'll be having this all over 32. Now you realize that they say after 15 days, what will be left? Remember, I'm recording this in days. My time is days. So after 15 days, I have 1 over 32 of the original value that is left, which is equivalent to, because they say that what is left is 1.55. So this is 1.55, what is left. So I'm going to clear this fraction. N sub 0 is going to be 32 times 1.55. N sub 0 is going to be 49 point. So the value, the original value is 49.6 grams. So this was the original value of this substance according to this question. And do I have that? Okay, I have option A as my answer. Thank you for being part of this class. Bye.